Happy week 4, everybody. I wanted to go over a few examples to kind of help you with the homework problems. Um, what I kind of see is um, I think if I just do some of these problems that are like covering everything, it'll kind of help because I know the first homework assignment just asks you to find the R values, the maximum R values, and the zeros, and then the second homework assignment asks you to put that all together with what you learned last week in order to graph them. So that's what I'm going to kind of look at. Is I want to look at some of the problems that would come from homework from homework 3, graphing polar and classic curves, the one that asks for the the type of curve, the symmetry, the max R values, and the zeros, and then the graph it, because I think that's going to actually help you in doing the other ones. So we are going to go ahead and look at that. Ooh, I just noticed that there is a question that we need to address. Hey, if you're watching this video, if you try to do number 13 on the homework, that's not going to work very well. We didn't talk about that. So, okay. So let's just take a look at a couple of them. Let's start with number 1, or this first one here. So if I had something like r equals 2 minus 2 sine of theta, and I wanted to determine a few things. I wanted to first determine the type of curve. I want to determine its symmetry, its max R value, and its zeros. Right? So one of the first things that I do is I need to figure out what kind of graph this is. So if you took a look at page 35, which I've got right in front of me, I kind of browse through this and I see that I have something in the form of a plus or minus problem. So that lends me to say it must be a type of limison, right? I've got these limisons that are a plus or minus b sine of theta. And we need to determine then what happens if I take a and b and divide them by each other. So if I take 2 and divide it by 2, I end up with 1. So whenever a divided by b is 1, we end up with a cardioid. And specifically, since this is a sine cardioid, I know that it's going to happen on the theta equals pi over 2 axis. And even more further, because this is negative, I know this cardioid is going to go down. So what it tells me is that if I had a graph, this cardioid is going to kind of look something like that, right? It goes in the downward direction, and it is on sine, so it's going to be on the theta equals pi over 2. So that kind of gets me going in the right direction. Now I can start thinking about some of the things that I'm going to need to actually solve this problem, like its symmetry, its zeros, its put this n back in here, and its max R values. Specifically with the cardioid, what I do know is I know that for my R values, right, there should only be one maximum R value, right? I shouldn't have multiple maximum R values because it's kind of like a circle, but it's a weird circle. It's a circle that gets close in one spot and then is big on one spot. So what it tells me is that this is probably going to be my max R value right about here, right? And for my zeros, I know that it should have at least one zero, but yeah, I mean, it's going to have 1, 0, right? It goes into 0 at one spot right here. It doesn't loop back around or anything until the end. So I'm looking really for 1, 0. Hold on, my dog wants out, of course. They wait until I'm recording, and then they're like, hey, now's the time for me to go outside. Okay, so symmetry-wise. Well, now that we know what these graphs look like, symmetry should be pretty easy for us. I can see that this looks like it's symmetrical over theta equals pi over 2, right? I can see that. Next dog. 1 dog, 2 dog, 3 dog, 4. I hear the other one. Is she coming? No. Okay. All right. So let's just test that, right? Let's just test if it does have symmetry over theta equals pi over 2. So to do that, again, I'm checking my notes because I don't have those totally memorized. Let me not screw this up. To check theta equals pi over 2, we're going to replace negative r and negative theta. So negative r equals 2 minus 2 sine of negative theta. I can already tell myself that this isn't going to work, right? This negative is going to come out, so I'm going to have negative r equals 2 plus 2 sine of theta. And then if I divide by negative 1, I'm going to have a negative 2 and a negative 2. There's the third dog. I knew she was coming. Done. 3 dogs outside. Now all 3 of them will want back in individually as well. Driving me nuts. Okay. So with that, I need to then test my other one, which is that r stays the same, and I replace my theta with pi minus theta. So we're going to have to do our difference of signs here. So 2 minus 2, and then we're going to have sine of pi, cosine of theta. Keep the sign the same, and cosine of pi, sine of theta. Okay. I know that at pi, we're at the point -1, 0. So cosine is -1, sine is 0. So what that tells me is sine of pi is 0. So this whole beginning part right here just becomes 0. Right? Done. Right here, though, this cosine of pi becomes -1. -1 times sine of theta is negative sine of theta. And then I have minus negative sine of theta. So this whole thing is going to turn into plus sine of theta. So I have 2 minus 2 times a positive sine of theta, so it doesn't affect that -2, and that looks the same as the beginning one. So yes, it definitely has symmetry over theta equals pi over 2. You could at this point test the other ones if you want to, but based off the picture and that I've just verified that the test works for the what that picture is, I know that I'm on the right track. I don't need to do the other ones. I can see that it's going to work. In fact, for this whole homework assignment, if you didn't test them, I wouldn't be upset, because at this point we now know how to test for symmetry. We did that last week. You don't necessarily have to test as long as you feel comfortable with looking at page 35 and picking out the correct picture. Alright, so my maximum R values. So maximum R values, again, can happen if I change sine of theta or sine of n theta or cosine, whatever it is, into 1 or -1. So let's start by changing it into 1. So 2 minus 2 times 1. If I did that, 2 minus 2 times 1 is going to give us 2 minus 2, which is going to give us 0. Let's also try changing it into a -1. So -2 times -1 is going to give us +2, and 2 plus 2 equals 4. So I can see right here where the maximum is. If this had been a -4, then they would both be maximums, because -4 is the same distance away from 0 as 4 is. But 0 is 0 away from 4, or 0 away from 0, and 4 is 4 away from 0. So I know that the -1 is the only one that's going to give us a maximum here. So ultimately, then, I need to know, great, when does sine of theta give us -1? Well, I know that sine of theta gives us -1 at this spot, my 3 pi over 2 on my graph. So I know 3 pi over 2 is my theta that I'm looking for here. So ultimately, and we'd said this, if it's a cardioid, there's only one max R value. I just said 0. I meant -1. Did I say 0? I don't know. 3 pi over 2 is the furthest point away from, and we know our cardioid has one maximum, which we did predict would be at 3 pi over 2. So I know that my first point is that we have a radius of 4 at 3 pi over 2. Okay? And last is to determine my zeros. So again, to do zeros, let me erase this again. To do my zeros, we're going to set everything in here equal to 0. That whole equation is going to be equal to 0. Okay, so I'm going to take this equation. I'm going to set it equal to 0. So it's going to become 0 equals 2 minus 2 sine of theta. So I'll subtract 2 first. Get rid of that plus 2 at the beginning. And so now I have -2 sine of theta is equal to -2. We'll divide by -2. That's going to cancel out. And -2 divided by -2 is +1. So +1 equals sine of theta. So I ask myself, well, great, well, when does sine give us +1? Well, that's going to be right up here, right? That's going to be at pi over 2. So I know that theta equals pi over 2 is our 0, which again makes sense. If you look at the picture we drew of our cardioid, we said that it should come back in as we get up here, right? You can see as it approaches here, it comes back in. So we know that we're going to have a 0 radius at pi over 2. And at this point, if you wanted to graph it, you could do a few things. You could plug in a variety of extra points, because I know it's symmetrical over theta equals pi over 2. I could plug in some points from quadrant 1 and quadrant 4, take all those quadrant 1 points and flip them over. You also could just use the fact that we know a little bit more about these graphs to kind of figure it out. I do know that at the very least that I now have a maximum. I go over 4, rotate 3 pi over 2. That's going to be right here is our first point. And then I also know that as I come into pi over 2, this is going to be our second point. So maybe let's just pick a couple points, right? Let's just plug in a couple. Let's try plugging in, we know that in between here, from 0 to pi over 2, eventually we're coming back into 0. So let's just try plugging in pi over 6, right? And I choose pi over 6. Actually, you know what? Pi over 6 is not. Pi over 3 is what I mean. Let's choose pi over 3 because I know that the sine of pi over 3 is 1/2. And 1/2 is easy to work with. 1/2 times 2 is 1. 2 minus 1 is going to give us 1. So I know that a radius of 1 will be at pi over 3. So that'll get us right here. So I'm on the right track to seeing what's going on here. I can also plug in 0. I know what happens at 0. Oh, and I also know if this is here, we know this is over here, right? We can flip it over here to 2 pi over 3. So I can see what's happening as it kind of starts to wrap out here. Okay, well, let's talk about what happens at 0, because I know the sine of 0 is 0. So that helps a little bit, because then I have 2 minus 0, which is 2. So I know that at 0, we're at 2, which means on this side, we're also at 2. So I can see this graph kind of starts to go whoop and whoop. And ultimately, now I just need to get myself to swing down here. And I think we have enough points at this point to make this kind of clear what's going on. There's our cardioid, little heart shape. So just by plugging in a couple points there, you can do that then with those extra pieces. And that's kind of the point of this. If you have an idea what the shape should look like, you know its symmetry, and we know its max R values and its zeros, it makes it really easy to figure out what that graph really should be doing. So let's look at another one. Okay, so what if we looked at something like 3 cosine of theta? Actually, I think that one's going to be a circle. Like let's pick something a little bit more challenging. I don't want to do some super easy ones and then leave you in the dark. That's another sine. You know, that one's a tough one. Let's do that one. We'll try. I'll do 2 more. This might be a longer video, but let's do 2 more. I have 2 more that I think would be worth looking at. So r equals 5 sine of 3 theta. What you're going to start noticing is that really, as long as theta is just theta, these problems are a lot easier. The moment that something turns into 3 theta, 2 theta, 5 theta, that's when they get really confusing, because that's when they start turning into the lemniscates or the rose curves, which are the ones that have these petals that kind of go woo, 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 right? Those are the ones that get a little bit crazy. The circles and the lemnisones are pretty easy. It's the roses and the lemniscates that are a bit tough. So looking at this one, the first thing I notice is there's a 3 theta. The moment this number breaks past 2, I know that it's not going to, like, if you have 2 theta here, it could be a lemniscate. But to be a lemniscate, it has to be 2 theta here, and it has to be r squared over here. If that number is anything other than a 2, or if it's a 2 and not r squared, you know it's going to be a petaled rose. So I know for my type here that it's going to be a rose. Specifically, since it's an odd number, remember odd numbers have the exact same number of petals. So this is going to be a 3 petal rose. Whereas if it had been like 4 theta, we know it would be an 8 petaled rose, because even numbers double their petals. Going in then and thinking about that. So let's draw our quick sketch of a graph up here. This is what our expectation is. Now, again, looking through this, and I don't know that I made this as clear as I could on the notes, you'll start to notice that anything that has a sign always starts with its first petal in between quadrant 1 and 2's 2.0 and 90, whereas cosines start on the polar axis. So, hold on, let me get this last dog in. It's not coming. I'm not recording this video either. You're just all gonna have to keep dealing with the me disappearing to let dogs in. Okay, back to what I was saying. Sine starts here, where if it had been cosine, it would start here, right? So just kind of keep that in mind, and then everything kind of gets evenly distributed from there. So since this is a 3-petal rose, I need to figure out how to evenly distribute that, and that's going to kind of cause essentially us to have to go a third. We're going to have to break this into thirds. So it looks like I'm going to have to go like 1.5 quadrants this way and 1.5 quadrants this way. So I think it ends up being, looks like it ends up being something like this according to the picture. Right, so it's going to look something like that for my sine petals. Give me 2 seconds here. So it doesn't start directly in the middle, and that's kind of the weird part. I guess sines are going to be a little bit tougher. Sines aren't as easy to figure out where they start, but 3-petal curves for sine are going to look like this. 5-petal curves are going to look like that for sine, so they start going up. I will look more into this because I actually, as I'm doing this, I'm not 100% certain how to determine where the sine starts. You do notice that this is still always in between 0 and 90. It just doesn't necessarily have to be directly in the middle. So I will determine exactly how that happens and let you know. In this case, though, we know that if I do this, I should get something that looks like this one. The reason I know it's going to look like that one is just based off the symmetry, right? I know this is symmetrical over theta equals pi over 2, which means it's going to have to go through here. So my symmetry is theta equals pi over 2. Great. So I know that everything's going to get reflected across that middle line, that y-axis, as we'll call it. If you wanted to test it, you could. I'm not asking you to do that, though, so we're good there. So let's go ahead then and talk about the first thing, our max R values. So again, to do max R values, we got to do two things. First, change the entire sine of theta, or sine of 2 theta, or sine of 3 theta, whatever it is, change it into a positive one, and change it into a negative one. And then solve those. And whichever one has the highest absolute value is the answer. Well, here's the thing, like -5 and 5 have the same absolute value of 5, right? That means they're both the same distance away from 0, so both of those represent our max value. Since r is a distance, radius is a distance, the negative doesn't matter there. So those are both going to represent that. So ultimately what I need to know is, when does, I keep writing sim, I don't know why, when does sine of 3 theta equal positive 1, and when does sine of 3 theta equal negative 1? Both of those are going to be valid solutions that we could use for this. So I think maybe an easier way to think about this at first is, let's start by just asking ourselves, well, when does sine of A equal 1, and when does sine of A equal negative 1? Well, sine is going to be positive 1 when A is equal to pi over 2. And sine of A is going to be equal to negative 1 whenever A is equal to, and that's going to be going down 3 pi over 2, right? So what that tells me is that 3 theta has to equal pi over 2. 3 theta equals pi over 2, and 3 theta could equal 3 pi over 2. So that builds in that extra step that we have to solve. So you solve it with pretending that there is no number in front of the theta, and then you pretend that there is a number, or then you add that number in front of theta after you figure out what it would be without the number. So don't even think about the number at first. Figure out what the numbers are first, then set 3 theta equal to that. So then over here, if I want to simplify this, maybe an easier way to do this, we would divide by 3, but dividing a fraction by a number is weird. Let's instead think about it like this. Right? I would cancel out 3 by multiplying by 1/3, because a third of 3 is 1. And then multiply this side by 1/3. So what I get then is theta equals pi times 1 is pi, 2 times 3 is 6. And down here, I would again multiply by 1/3. And I know that theta gives me 3 pi over 6. Here's one thing I want to point out, though. If you look at that picture, we know it's a 3-petal rose. How many maximums are there? Well, there's going to be 3, right? There's going to be a maximum here, and a maximum down here. So when I go to graph this, I probably want to get 3 maximums to be able to do this correctly. I want to know where all 3 maximums happen. So I would actually want to find another one. Oh, I didn't even finish this, y'all. Whoops. 3 pi over 6 simplifies, right? Both those divide by 3, so we get pi over 2. There. Simplify your problems. So we got one from a positive one at pi over 6. Then the next one happens at pi over 2. Well, let's find another one. You're going to go small, big, small, big, small, big. So like if we got one from this positive one, then we got one from this positive negative one, now let's get another one from positive 1. So again, when else would theta equal positive 1? Well, that's only happening in one spot in the unit circle, but remember we have multiple representations of that, right? If I come around to here once, we're at pi over 2. But then if I go around again, I could add 2 pi to that. So we also know that this would be 5 pi over 2. 5 pi over 2 would be the same thing. Remember, it's pi over 2, 3 pi over 2. 5 pi over 2, 7 pi over 2. 9 pi over 2, 11 pi over 2. And you just keep adding a pi to it every time, which ends up being 2 pi over 2. So I know that I could also get the solution at 3 theta equals 5 pi over 2. Again, multiply both sides by 1/3. Cancel. Over here, cancel. So I also know that theta is going to give us a maximum positive 5r value at 5 pi over 6. So with that, I've got 3 solutions, and I didn't do a very good job of writing this in nice spots, so I'm going to put these over here. Let's do this. Max r. Okay, so I have a max r that happens positive 4 at pi over 6, and that's this one here, right? This one, be careful. When we plug in pi over 2, we get 3 pi over 2, which gives us a negative 1. So I'm going to have a max r value at negative 4 and pi over 2. That's this one here. And then last, we're going to have a positive 4 again at 5 pi over 6. There we go. So now I have my 3 values. Again, make sure you use the value after you divide by 3. You want to use the values for when you have theta equals, not 3 theta equals. All right, let's clear some of this off now so that we can do our zeros. Nope, I don't want to clear the symmetry. Clear, clear, clear. Let's see if I can just clear this and that. Yes, did it. Okay. So now we're going to go ahead and get our zeros. So for 0, again, we just set this equal to 0. So 0 equals r sine of 3 theta. And I don't know why I put r, 5. Divide both sides by 5. It doesn't really matter, though, because 0 divided by 5 gives us 0, and then I get sine of 3 theta. So we've got to ask ourselves, well, when does sine of a equal 0? Well, sine of 0, or sine equals 0 in 2 places, right? Sine is 0 at 0 degrees, or 0 radians, and sine is also 0 at pi. So both of those are solutions. So I'm going to come back here and I'm going to say, great, 3 theta could equal 0, or 3 theta could equal pi. Now, one thing you do want to be mindful of here, and I think this is where it can be a little bit confusing, is your zeros is technically the way they did it in the homework, and like when I post the answers next week, what you'll see is they gave every single 0 in between 0 and 2 pi. They went through and did all of them. You might not need to do that for graphing, though. You might not need all of them. For the sake of just making sure we're being thorough, let's find all the zeros, right? So when I do these dividing by 3's, right, 0 divided by 3, let me put that in pink. When I divide this by 3 to get rid of the 3 over here, we're going to get 0 as one of our solutions. So I'm going to just put all those solutions over here. So theta could equal 0, right? Theta down on the bottom for my negative part when I divide by 3, I'm going to get pi over 3. You can see that that only covers the first quadrant of the unit circle. So let's think of other spots that we could get 0. Again, that's just when we add 2 pi, right? So we'd also get 0 at 2 pi, and we would get 0 at 3 pi. So putting that over here and dividing, 2 pi divided by 3 would give us 2 pi over 3. And putting it down here and doing 3 pi divided by 3 would give us, well, the 3's cancel, we get pi. So you can kind of see what's happening. 0, pi over 3. 2 pi over 3, pi. You may be able to make the rest of the predictions, but let's just keep going for the sake of the people who may be still a little bit confused. Add 2 pi up here, we get 4 pi. Add 2 pi here, we get 5 pi. Again, those are still falling on this 0 and this pi line, so they still have sine of 0, so they're still valid solutions. That's the hard part about polars. There's so many solutions because you can repeat the number over and over and over again, right? So 4 pi divided by 3 and 5 pi divided by 3, none of those simplify, so we're going to have 4 pi over 3, 5 pi over 3. And lastly, we can add and get 6 pi here and 7 pi here. So I end up with 6 pi over 3, which would simplify. This cancels. This becomes a 2. So I have it at 2 pi. And I think that might be the last one, right? Because 7 pi over 3. 7 pi over 3 is going to put us at bigger than 2 pi. So don't need that. So technically, all the zeros are all of those things. But you're going to see we probably don't need all those to graph it. So let's go ahead then and work on this graph. We know that we're starting our maximums, right? So go over 1, 2, 3, 4 up to pi over 6. That's going to be our first maximum. My second maximum, we're going to go -4 and then rotate pi over 2. So ultimately, that's going to put us down here because that's pi over 2 away from -4. Even though that's at 3 pi over 2, that's okay because I started at -4, meaning this is only a pi over 2 rotation, not a 3 pi over 2 rotation, because this was my starting point. If I started over here, then it would 3 pi over 2. But because I started at that point, we're only at a pi over 2 rotation. We do that. All right, and the last one is to go over 4 and then rotate 5 pi over 6. That's going to put us over here. So those are the maximums. Like I said, at this point, you probably have a pretty good idea what's happening, right? We know that we expect this to come out and then loop back in. We then expect it to come out and loop back in, and then come out and loop back in. You could plug in those other numbers if you want to make sure that you're doing this correctly. What I'm really looking for, though, here, if I want to be as accurate as I could, right? What I'm really looking for is that between 0 and 2 pi over 3 for this first, or 0 and pi over 3, sorry, 0 and pi over 3. So between here and here are the zeros. So I know that that first petal should kind of come out here and stay really close to the edge, but then nope. It would get really close to this edge inside and then come out and then come back and get really close to the edge, kind of like little asymptotes, right? My next zeros are at 2 pi over 3 and pi, so 2 pi over 3 is going to be here, and pi is going to be across that bottom. So as this leaf comes out, it's going to get close to this edge and then come over here and then get really close to that edge again as it comes in. And then my last zeros were 4 pi over 3 and 5 pi over 3. So here is 4 pi over 3. Here's that 5 pi over 3. So that's where my zeros are. So as it gets here, it goes to 0. So it's going to, again, come in close and get close to that line before it hits 0. And come in and get close to that line before it hits 0. And that would be your 3-petal rows. All right, I know we're at a super long video, but I want to do one more just so that we have a really good resource to look at for this to help you throughout the week. I don't want you stuck and confused and stressed because this is hard. Okay, I want to do one more here. Let's look at 5 cosine of 2 theta. R equals 5 cosine of 2 theta. Again, I see a number in front of theta, and that tells me that I'm going to have some trouble here, right? So looking at my things that I need my type. What? You were just out. Just out. Come on, Pepper. Do you want to go out or not? I'm just leaving the door open. I'm leaving it open. I'm going to let the bugs in. Okay, type, symmetry, max R, and my zeros. Okay, so again, looking at this picture, I recognize there's a 2 theta here, so I instantly look at lemniscates, but R isn't squared, so it's not going to be a lemniscate. I know then it's going to be a rows. Since it's an even rows, I'm going to have to double it. So I know that this is going to be a 4-petal rows. Okay, being that it is a cosine graph. Cosine graphs are a little bit easier to think about because their first petal is always starting right here. And so as 4 petals evenly distributed is going to be 1 on each axis, which is pretty nice. And even further, you may be able to do a lot here, right? If this is the case, we know where our maximums are, right? Like the maximum here, if we plug in our number here, we're going to get R equals 5 times 1 and R equals 5 times -1. Well, 5 and -5 are the same radius, right? Just one goes opposite way. They are the same radius. So I know that I'm going to have a maximum of 5. And I know that I have 4 maximums at 5s. And just based off that picture, I know where they're at, right? Like one's going to be at 0. One's going to be up at pi over 2. One's going to be at pi, and one's going to be at 3 pi over 2. I know that's going to happen. Now, if we want to verify that, we could go in and do our max R values like we normally do. We could say, okay, cosine of 2 theta is equal to 1. That's how we get the positive 5. So we'd ask ourselves, great, when does cosine of A equal 1? Okay, well, cosine of A equals 1 at one place, 0, when A is 0. So then I can come over here and say, great, 2 theta has to equal 0. So if I divide by 2, I get theta equals 0. Well, what's another name for 0? 2 pi. So I can come over here and I can say 2 theta equals 2 pi. Again, divide by 2, and I get pi. So I have two solutions there. It's going to be positive 2 at 0 and pi. So my max R values would be 2 when I rotate 0 and 2 when I rotate pi. Think about if you graph those out. Oh, it's not 2. I'm sorry. It's 5. I don't know why I put a 2 there. I don't know where I got 2 from. The maximum is 5. I think I got the 2 from in front of the theta. There we go. So out 5, 0 rotation, that's our first point. Out 5, a pi rotation, there's our second point. Boom, that makes sense. Okay, what if we did the cosine of 2 theta equals -1? Well, we have to ask ourselves, well, when does cosine of a equal -1? And that's going to happen whenever a is equal to pi, or if we pick a second one, 3 pi. So again, coming over here, 2 theta equals pi, divide by 2, divide by 2. I got pi equals pi over 2, or theta equals pi over 2. You also could do 3 pi and divide that by 2, and you get 3 pi over 2. So then let's put those points here. We get a radius of -5 when I rotate pi over 2, and a -5 radius at 3 pi over 2. Okay, so we go -5, rotate pi over 2. Again, that's going to put us down here. And if I go over -5 and rotate 3 pi over 2, that's going to put us all the way up here at the pi over 2 spot, which is right there. So you can see those pop up right there. So as you get better at this, you may not have needed to do all that work because you recognize where those maximums are going to be. And I know I skipped symmetry. I don't know why I did that. I just got ahead of myself, I think. In terms of symmetry, we know that this graph is going to have, whenever you see a graph like this that has like this polar symmetry, this theta equals pi over 2 symmetry, which then tells us it also has pole symmetry. So it's going to have all three. And the last thing for me to concern myself with is these zeros. And that's a little bit harder to just make up off the top of your head. So let's put those in. Again, this one, we kind of recognize that we should have like 1, 2, 3, 4, 5-ish zeros, I think. Again, let's just do what we did on the last one, though. Like, instead of worrying about how many zeros I actually need, let's just put all the zeros from 0 to 2 pi. That way we're making sure we're touching everything the homework says that we should touch. So we divide by 5. And we'd get 0 equals cosine of 2 theta. Again, come over here and do a little aside. Okay, well, if cosine of A equals 0 when? And cosine of A equals 0 in two spots. Whenever A is pi over 2, and whenever A is 3 pi over 2. So I'm going to use both those numbers in solving this. So let's start by saying, okay, 2 theta equals pi over 2. And we divide both sides by 2. And again, let's not divide by 2, because dividing a fraction by 2 is weird. Like, you could remember to multiply by the reciprocal, but I'm just going to multiply by the reciprocal off the top, off the front. So I multiply by 1/2, that cancels out the 2, and I get theta equals pi over 4. Okay. Well, I also get 0 at 3 pi over 2. So we're going to have 3 pi over 2. Again, we multiply both sides by 1/2, and I end up with 3 pi over 4. So far I've got a 0 at pi over 4 and 3 pi over 4. So it looks like I need to do this 2 more times to get these last two zeros. So we ask ourselves, great, well, when does pi over 2, what's the same thing as pi over 2? When I add 2 pi, right? So if I add 2 pi, then I'm going to be at 5 pi over 2. When I add 2 pi over here, I'm going to be at 7 pi over 2. Do the same thing, multiply those by 1/2. I'm going to just kind of shortcut a little bit here because we see the pattern. The bottom's just getting bigger by times 2. So I end up with those two answers. Nope, not that. That. So I know my zeros, to make this not blend in, are going to be at 0 pi over 4, 0 3 pi over 4, 0 5 pi over 4, and 0 7 pi over 4. So again, if I drew these lines right here, just like dotted lines to kind of help guide me, right? I know this is where it should get, that's the wrong one. I know this should kind of help guide where this is going. So what I know is as I go to graph this, that as it comes in, it gets closer and closer to that line until it gets to 0. And it gets closer and closer to that line until it gets to 0. Again, you could plot some extra points here if you want to, but you really don't need to if you're just sketching these. Alright, there and there. These leaves should all be the same size, by the way, but that's kind of tough to do on this digital pad. I guess that one looks kind of like the top one, right? That one came up pretty decent. That one came out. It's just the right side that looks kind of dumb. And that would be it. That would be your 4-petal rose with your important details there. So again, I hope this helps a little bit. I know this is a very big topic and a lot to do. Just be patient. Ask me your questions. Come to Zoom office hours if you need it. I'll be here to help you. All right, talk to y'all later. Bye.